All right. Good evening, everyone, and welcome to the January meeting of the Ottawa Centre Royal Astronomical Society of Canada. I hope everyone had a fantastic holiday with lots of celebration. We've got a fantastic program in store for you today. We'll start off with Dave Chisholm giving us a rundown of the Ottawa skies in January, and hopefully it'll be more than just clouds. Second, we'll have Dr. Lockie Scott giving us Canadian Space Situational Awareness briefing. Then we'll go to the break. We'll have an update on some international outreach. And Tim Cole will be taking us through the exciting lunar eclipse coming up at the end of January. And then we'll have our observations and observation challenges. And then other various announcements. So here are new members for the past month. Welcome, new members. Thank you for joining. And I suspect the next month we'll have the list of members for 2019. But we had 60 new members in 2018, so that's fantastic. Alrighty, members in the news. Can't see over here, but it's a picture from Peter and Deborah Saravola. That's awesome. Yep. All right, that's it for members in the news, and I'll hand it off to Dave to take us through Ottawa skies.
There you go. Okay, thank you. Okay, I can't promise no cloud cover. It's that time of year. But let's take a look at the skies. So this is the lunar calendar for the month, and of course you see that special orange moon there. Everybody's probably aware of this with the lunar eclipse from the 20th to the 21st. That also happens to be what they call a supermoon. It's closest to the Earth. This is the first of 3 supermoons in 2019, the others falling on February 19th and March the 21st. Because we're getting a very long and detailed presentation later on the lunar eclipse, I'll just quickly skim by this slide. You need to be up and awake at 12:12 for the full effect. We have the Quadrants meteor shower. It happened last night, but of course it's around that time. And 40 meteors per hour. And with no cloud cover, the moon will be a thin crescent, and it should be a good time to view them. Mercury is not visible. Venus is visible in the early morning, and the greatest western elongation is on January the 6th. Mars is visible the first part of the evening. Jupiter is visible just before sunrise. There's a conjunction of Venus and Jupiter on January the 22nd. The 2 planets will be 2.4 degrees apart in the early morning. Saturn is not visible. Uranus is visible all night, and Neptune is visible the early part of the evening. And there's our cartoon of the month. Thank you.
Thank you, Dave. All right, up next, we're going to have a presentation from our special guest, Dr. Lockie Scott. Dr. Scott is the lead scientist in Space Situational Awareness R&D project at Defence R&D Canada, and is the principal investigator on the NEOSAT Space Situational Awareness R&D mission. He has 16 years experience developing automated robotic telescopes for SSA and research operations of small orbiting space telescopes designed for space surveillance. So Dr. Scott will be giving us an overview of Canadian Space Situational Awareness research and development activities at Defence R&D Canada. Dr. Scott.
Thank you very much. I'd like to thank everybody for the opportunity to come talk today. And we're going to be talking a little bit about something, a little bit of a variation on astronomy, how we basically apply astronomy to a defense and security area. I never thought that when I'd be doing my undergraduate studies, that eventually I would evolve my career from a path of engineering merge astronomy, aerospace engineering, a little bit of space sciences, and start looking at the orbital environment above us as basically the cornerstone of my career. I'm going to talk to you today a little bit about some of the space situational awareness projects we've been doing. I run one microsatellite. I'm the principal investigator on NEOSAT's SSA mission. I also do quite a bit of work on the Sapphire mission as well. And basically what I'm going to give you is a very much a fire hose treatment of SSA in the last 10 years. I say this is SSA for the last 10 years because you guys have your meeting on the regular time when I usually play hockey each night. So anyways, you're going to see basically what we've got to for quite some time. So the problem is pretty big. I don't look at stuff that's too far out into space. 40,000 kilometers is about as far as we go. Everything in green is the stuff that mankind has put there, and that's the stuff that on a day-to-day basis, Canadian forces has to care about to know whether or not something might fly with a satellite in orbit. Canada has satellites out there that provide communications, they provide missile warning, they provide navigation, and basically a lot of services to even to civil society that are very, very important. And what we really care about is making sure that they're there. There's so much debris in space now, we have to care about this. The Canadian Space Agency vets collision warnings every day, and we have to actually figure out whether or not those dots are actually going to intersect in orbit. And that's a big problem. One telescope's not going to do it, a lot of them don't. The problem is changing too. Next slide. The security in space, the security situation in space is changing. We're starting to see the reappearance of anti-satellite weaponry. And what you're seeing here is the actual trajectories and orbital paths of the large fragment debris spawn that came off of the Chinese anti-satellite test back in 2007. You can see where Canada's radar sats started doing these spawn dives within one orbital revolution of that event. That's how much energy is tied up in these objects. When they collide at 7, 10, 15 kilometers per second, they cause catastrophic damage to these vehicles that we put in orbit. They cost tens or hundreds of millions of dollars a piece. And we have to start worrying about the third-party effects when something like this goes on. There was another event that happened about 2 years later where two satellites accidentally collided. It wasn't an intentional event like this one. And we have to start dodging those events. And as more and more debris starts building in orbit, we have to start monitoring it more and more frequently to make sure and vet that these collisions aren't going to happen. So the Government of Canada's engagement in SSA started out with national defense and Canadian forces. We used to provide telescope observations with the Baker Gun telescopes located in St. Margaret's, New Brunswick, and Cold Lake, Alberta. These telescopes were film-based. They lasted about until the 90s, until CCDs came along and those film-based systems became obsolete. In the 1990s, the Canadian forces contributed personnel to the missile warning radar community that basically doubles as the space surveillance tracking capability for the United States Space Surveillance Network. But in the 2000s, we got back into the game again. We started building telescopes, but recognizing, just as much as I knew what you do, putting a telescope on the ground in Canada is not much fun when you're trying to see stuff in space. You always have to deal with clouds. So we put ours in orbit. And we put two of them in space, Sapphire and NEOSAT, and I'll talk a little bit about those later. The Canadian Forces also has a protect and defend role in regarding Canadian space systems of national interest. Therefore, we have to monitor and track objects that are our own and our allies in space, making sure to protect. The organization that I come from, DRDC, I work at DRDC Ottawa. It's located out in the west end of Ottawa. We're kind of tucked away around where the old Martel buildings used to be out there. My very small group out there has the job of doing research in space operations, which is basically understanding what's happening in space. We also we built the ground-based optical telescopes, which are an array of network telescopes that contributed data operationally to the Space Surveillance Network for a few years. But more recently, we've been doing work with the NEOSAT microsatellite, which is a space-based telescope, small aperture, quite affordable, and a lot of fun to use like that. And we've been using this system to basically do this kind of measurement in situ in orbit. The Canadian Space Agency also has a role to play in this field. The CSA is a operator of satellites for the Government of Canada. They have to vet and monitor collision warnings for any of the satellites that they operate. And for the satellites that do have the ability to maneuver, sometimes they will issue a forecast. So this is where every close approach for 4 years happened back in from the time span of 2010 to 2013. And you can see that in low Earth orbit, mostly hugging the Earth under 1,000 kilometers, we concentrate mostly over the North and South poles. That's just because most satellites tend to be highly inclined orbits. They tend to have their orbit paths cross those locations. So that's where most of the low Earth orbit conjunctions occur. Canada has a lot of satellites located out in geosynchronous orbit. Telesat Canada and SEAL operate assets out there, and they do so not just above North America, but right around the world. You can actually see there's a few dots out over Asia here. So it's important for us to have a lot of understanding, not just above North America, but to actually be able to track over longitudes that are not, they're on the other side of the planet. And that's where space-based capabilities come into play. The area that Canada is responsible for tracking objects in space is that deep space mission area. We're tracking out in geosynchronous orbit. So a lot of the imagery and stuff that you're going to see here is mostly looking at geosynchronous satellites. The Space Surveillance Network is the U.S. affiliation of sensors that has the job of tracking all of this stuff in space. And it's basically an arrangement of about 20 plus sensors all over the world. And its job is to basically track all those objects using both radars and telescopes. The missile warning radars of perimeter North America, they primarily track all the stuff that's close into the Earth, low Earth orbit. They basically beam out energy, they hear a radar echo, and they basically say how far away an object is. The machine that you see on the right is called GEODs. These are the electro-optical telescopes that the U.S. Department of Defense operates for tracking geosynchronous orbit. They're about 1 meter class instruments. Had the opportunity of actually sitting in the dome with one of these things operating, and it's quite a remarkable machine to see in operation. The servo motors that drive this thing, they're probably about 3 or 4 horsepower apiece, and you can hear these things cranking over, driving that big one-ton instrument around. It's pretty impressive to see it in operation. But anyways, these are the telescopes that are used primarily for tracking stuff farther out. Telescopes are more efficient for looking at things deep out in space. The sun is the illuminator, and we see the reflected sunlight back on the ground, and that's how that works. Now, Canada has to do things a little bit differently. Who here has actually gone out on any given night, actually saw the sky? Here. So, all right, so anyways, we had to engineer around this a little bit. So the best thing we could do is let's put our telescope on a small satellite, and we did this twice now. So Sapphire is the operational capability of national defense. It's a capability that we're always transmitting observations on deep space satellites on orbit. It can see down to objects to magnitude 16. So just to translate that into satellite size, that's about 1 meter objects, about 40,000 kilometers away. It's pretty sensitive. The accuracy of it is about 1.5 arc seconds. If you were to, when I'm explaining this to the Canadian Forces and the Air Force, they usually say, well, basically that's a sniper able to hit a loon at 4.2 kilometers. So that's pretty much the accuracy in terms of angular accuracy of this thing. It's fast out of 22 Wing North Bay, but this sensor in the middle here is Neosat. This is an R&D capability that I'm the principal investigator for. It's a dual mission microsatellite. We built it to look at satellites and to look at asteroids. And we'll talk a little bit more about that later. We also own 3 ground-based telescopes. They're robotic. They're located in Alberta, and there's another one in Belcarche, Quebec. We have one here in Ottawa too. And these sensors are primarily used for R&D now, but they were contributors to the Space Surveillance Network for some time ago. We're moving away from classic CCDs, though. We're moving into very high frame rate cameras like EM-CCDs or CMOS, or even in some cases infrared. So this is what the imagery looks like. It's not the prettiest astro photo that you've probably seen here at these meetings. These dots that you see here are 3 Canadian geosynchronous satellites. They're about 45,000 kilometers away. It's the F1 cluster of 107 miles. And these satellites are basically broadcasting communications and satellite internet and Viasat internet and so forth back to the ground. You'll notice that we streak the stars in the background. That's intentional. That's because we want to concentrate that starlight on a small little set of pixels to find those faint little satellites far out into space. So we have to do this in order to see it with these small aperture instruments. Now once we actually take an image like this and put it into the computer, centroid, the centers of the dots and the streets and all these images, we transform it into right ascension and declination, the same thing that you guys deal with all the time with those telescopes and time. We package all that up, we transmit it off to the Canadian Space Operations Cell, and they can put that into an orbit estimation tool that will basically forecast the positions of these satellites in the future, and that's the whole name of the game here. So this is the ground-based optical telescopes. We built this starting in 2002. We finished it actually in 2011. It took us a while to get the system right. The sensors were contributors to the Space Surveillance Network for about 3 years up until the launch of Sapphire. When Sapphire was launched, we had to shut the sensors down operationally because the funding was cut off. Anyways, that's just the way the economics of that work. The sensors are basically the same thing that you'd use for high-end amateur astronomy equipment. It's the same thing that you'd use. We're starting to break into some new technologies with these sensors. We're using EMCCDs on the sensor here in Ottawa right now. We frame about 20 frames per second to try to twinkle the sky now to do some specialized observation with satellites that get really close together far away. We're starting to see satellites doing that. They're starting to interact in space right now. On-orbit servicing and those kinds of things are starting to take place. So we have to use different technologies now to do so. My favorite, though, is up in Valcartier, this observatory here. We have a shortwave infrared camera on the back of that one. This one operates during the day now. I don't have to get up at 2 in the morning anymore to go looking for a satellite that's going to pass overhead at a certain time. We can actually start running these sensors during the day. And right now we're seeing down to about magnitude 9 right now with the sensor in Valcartier. So this is some imagery of an event that happened last year. This is the AMC-9 satellite. It's a geosynchronous satellite that mysteriously jumped in altitude by about 10 kilometers and started drifting and spiraling uncontrolled out of geosynchronous orbit. Yes, this does happen with $200 million satellites. So it does occur. And it occurred actually 4 times in 2017. The satellite in the lower right is NMX-6. And AMC-9 actually did spirals around 2 other Canadian satellites during its little drift, uncontrolled drift out in orbit until the operators were actually able to get that satellite under control. Now you might notice something about AMC-9. You see that it's kind of changing brightness? We rely on that. If you take the photometry of that satellite, you'll see that it's periodic. And when I look at light curves from satellites like this, I immediately know that if I see a variation of greater than a magnitude or more, that satellite is uncontrolled. So without even having to talk to the operators, I can just basically take the light curve in that satellite and basically find out whether or not it's under control or not. So a lot of the equipment that you're using, you can infer this stuff yourself if you decide to take the time and the patience to actually sit down and record this kind of thing. You'll see a lot. There's a lot happening just 40,000 kilometers or less right above you. So I talked a lot about geosynchronous orbit right now. I'm going to lower altitude a little bit. Last year, we had the opportunity of watching a satellite, a nanosatellite, was operated by the University of Toronto, actually change shape. I think everybody here might have heard about the nanosatellite explosion that's happening right now. There's a lot of small satellites that's basically heading into low Earth orbit. These platforms are really cheap, and we're getting a lot more operators who are starting to put them into orbit right now. And it's creating some really neat commercial businesses and so forth. And it's pretty cool stuff. The problem is these things, when they're about the size of a loaf of bread, they're basically little cannonballs when you put them on orbit. And when you put them at about 800 kilometers altitude, they will want to stay there for a very, very, very long time. So you basically are putting long-term debris in orbit. So back in 2010, we invested some money into the University of Toronto to basically try out something with the CanX-7 nanosatellite. And it was pretty simple. Just put a drag sail on the thing, grab that rarefied, tenuous upper atmospheric gas that's up there, and try to pull it out of orbit. And that was one of the intentions of this experiment, and it's working right now. CanX-7 deployed the sail last year, and we're seeing it drop out of orbit at a rate of about 50 meters per day right now. We're expecting it to be under within 3 years. Now, before we get to that finding, though, we actually watched CanX-7 deploy the drag sail and coordinating the experiment between ourselves at the RASC, the University of Toronto, and the Royal Military College. And when CanX-7 was flying over Canada, I took the the observatory from Washington X7 rising over the horizon, and we basically track the object during the first sail deployment. Now, one thing I just want to set expectations here, we don't see the sails in the video, we just see the dot. That's basically the technology that we have to live with, unfortunately. But anyways, we were able to actually see the nano satellite change shape. To me, that's really important because small satellites changing shape or reconfiguring themselves is something I want to know about. And especially if I got a Canadian satellite doing it, I was willing to pay a little bit of money to actually do this. So what I'm going to do is going to show you what we recorded that day. What you see on the left here is basically the frames from our telescopes on the ground. This is from the Ottawa telescope, and this is the light curve generated from the satellite. And this is just an animation put together in satellite toolkit to basically show it in place.
I am arming the minus 7 sail.
That's the University of Toronto speaking.
Yeah, arm. Sending the fire command in 3, 2, 1, fire.
You hear the dome rumbling in the background. Magnitude increase of 2, just brightened by 2 magnitudes. RMC, can you confirm brightness increase? Confirm optical change on KMX7. Looks like the first sail deployed, guys. Congratulations. So the next time you're out looking at the stars, don't always think about everything's happening light years away in terms of what you're looking at. There's a lot of cool stuff that's happening just a few hundred or even 1,000 kilometers above you, and the Canadians are all over it, just so you know. So I'm going to talk a little bit about the space-based stuff that we work with right now. So Sapphire is the operational capability of national defense. This is a satellite where we have Canadian Forces officers and non-commissioned members actually operating on a day-to-day basis. This satellite, under that red baffle that you see there, is actually a 15-centimeter off-axis 3-mirror astigmat telescope, which is designed to basically work in the low Earth orbit environment to track satellites in deep space. The images it produces looks a lot like you see on the ground, except they can be a little peppery because of the radiation environment of that. It's about the size of a washing machine. It's probably the most elegant description I can basically say of the vehicle. It's pretty impressive build. It flies in a sun-synchronous orbit of about 786 kilometers, so it's not really that high up. If you track it with your own ground-based system, you can actually see it on your ground-based telescopes if you wanted to look at it. It can see about 360 objects in about 24 hours. It produces about 6 images per frame, and every 10 seconds or so, the satellite is snapping an image of geosynchronous satellites and then transmitting that data back down to the ground segment where the operators will take the imagery, convert it into observations, and send it off to the U.S. Space Surveillance Network. The U.S. Space Surveillance Network takes that data, they transform it into a prediction as to where those satellites are going to be in the future, and we just keep on doing this day in, day out. So there's probably about 4,000 objects that we track with Sapphire every 2 to 3 days. So Sapphire is, of course, is a part of a larger system. The sexy part of any satellite system, of course, is the satellite, but you are nothing without those ground-based antennas in the ground system. So these are the key parts that run the system. We have one antenna in Guildford, England, and there's another one in Abbotsford, BC, which downlinks data from Sapphire. It goes to the data processing at the Richmond facility in Detweiler. The data is shot off to North Bay, just about 3 hours from here. Canadian Forces members will process and transfer the data to another network that goes down to the U.S. Space Surveillance Network, and the U.S. Joint Space Operations Center receives the data, and we keep on participating in that out loud in the network. So now I'll talk about the other space surveillance sensor that flew with Sapphire on the same rocket. NEOSAT stands for the Near Earth Orbit Space Surveillance Satellite. It's a pretty long acronym, but basically what it is, it's an R&D microsatellite where we were testing microsatellites to do a militarily useful job in space. The project is a joint project between the Canadian Space Agency and We got the money because we want to test the microsatellite platform as basically as a way for the government of Canada to do experimentation in space cheap. Now, the big difference between a large satellite and the microsatellite class is you may look at them and say, well, there's not a lot of physical differences, but internally, we're actually using commercial grade electronics in there. This is the same kind of electronics that's largely controlling the engine computer of your car, actually. So there's a lot of similarities there. They're single string, we don't have a lot of redundancy on board. But inside that package is basically a computer and a lot of other parts that controls the telescope. So you can steer that telescope pretty much every day looking at interesting things happening up in the geosynchronous orbit. There's two objectives. One was to test the microsatellite platform for doing deep space catalog maintenance, or basically sustaining and tracking the orbits of objects in space. And the second one was to do space-based experiments that you can't do from the ground. So it was great. We got the money for doing this. We put the sensor in space. It's a great place to be doing space situational awareness. You're actually sitting in situ with the things that you wanted to actually take a look at. So this is what the instrument looks like when you take the solar arrays off. It gets kind of bland looking when you take the solar arrays off, but the major equipment that you're seeing here, we have a baffle that basically shelters a lot of the bright light that comes off of the limb of the Earth when we're tracking objects in space. It's got an aero-glazed paint on the interior of that baffle, and I looked down the baffle once during testing at the David Flora lab right here in the West End, and it's kind of creepy because you see this mirror kind of floating off in the distance, but you see nothing else around it. It's kind of creepy to see something not black surrounding something. The telescope is under this MLI tinfoil material that you see there. It's a 15 centimeter telescope. It's a 6-inch maxitop that we're flying in orbit. We cool the CCD using a radiator. I think everybody here is familiar with the little thermoelectric coolers on the back of the CCD, and that leads heat away from the CCD on most of your telescopes. There's no air to move in space, so we rely on conduction and radiation to dump heat into the ambient environment. So we have to use these special surfaces for doing that. The avionics, command and data handling, power, attitude control system, tracking, telemetry control, it's all sandwiched in this stack of avionics packages here. And that forms the backbone of the Neosat. And that's basically what controls and steers and operates the instrument in space. This is where we basically look in space. We track geosynchronous objects pretty much anywhere in this belt, except in here. That's the red zone. That's looking towards the sun. So I think everybody's first rule of the telescopes is you do not look at the sun with your telescope. The second rule of telescopes is do not look at the sun. Well, same thing in space. We don't want to blow the Neosat with it. So anyways, we always stay outside of the solar exclusion zone. And we can track pretty much anywhere else as long as we have stars in the background to track them. So what does an image from Neosat look like when it comes raw off the detector? Pretty hideous looking, isn't it? What you're seeing is 5 years worth of radiation hits on that detector sitting in that radiation environment in space. So we've got a really good video at the end here showing you why that occurs over time. The speckling that you're seeing here is basically high dark current that comes because of a CCD crystal, the crystalline lattice in your CCD basically gets bombarded by high radiation charged particles continuously, and they generate dark current at crazy accelerated rate. We do have a shutter on board the Neosat to mitigate it. We actually do a different trick to do this. What we do is we take 6 images like this, all in quick succession, and then we basically take what we call Neosat's dark, which is basically the minimum of the pixels in each one. That basically gets rid of most of the hot pixel and dark current, hot pixel content in the image. Check the mic there for a second. From there, we do a Fourier transform and match filter. This is just basically a mathematical trick that we play to figure out where the stars are in the background. And from there, we basically use the orbital data on the satellites that we're tracking to basically find the satellites in each image, and we form our observations. We send that off to the Canadian Space Operations Center or the other researcher that wanted that data, and that's how we form observations. It's pretty simple. The image processing code was written in MATLAB. It's called SQUID3. It stands for Semi-Quick Intelligent Detector. I don't come up with these acronyms, so I think someone else will want me to do that. So anyways, this is basically the overall sequence of events that takes place when we look at the imagery. seconds at one spot, it goes off to another spot, it goes off to another spot, and off to another spot. NeoSat's a little different. We operate the satellite by watching a couple of satellites and staying and dwelling on them for long periods of time. Last summer, we did that to our advantage. We were able to look at the AMC-9 satellite that we already knew was having trouble in orbit, but we were just basically doing follow-up observations on it. But we found something unexpected. This object, see here, didn't correlate in the catalog. And what we detected was a piece of fragmentation debris that came off of AMC-9 that was released probably about a day or two prior. So by following and keeping an eye on objects in space, by situating your sensors above the clouds, so you have the opportunity to frequently revisit these objects, we're able to pick out something that was falling apart in space. U.S. observers also saw this event too. They saw it. The object actually disappeared a short time afterwards, though. It's believed to be a piece of frost or something else that may have actually vaporized or ionized in space after it was released. They're not entirely sure what caused it, but it was large and bright, whatever came off of the satellite. So now I'm going to talk a little bit about some of the advantages of being in situ with your satellite. I talked earlier about conjunction, satellites getting very, very close to one another. Well, I'm going to show you an example of what one of these looks like, but it's from the point of view of NeoSat. But every week, we get a warning from the U.S. Strategic Command saying, your satellite's about to be destroyed. Well, thank you, that's $25 million that we spent. But anyways, basically every week we'll have an event where NeoSat will get close to another satellite. And this is one that we saw last summer. This is the Spot 2 satellite hurtling towards NeoSat at about 12 kilometers per second. What you see on the right is this blob, which is Spot 2, bloom saturating our detector on NeoSat. It got so bright that it starts throwing internal reflections in the telescope tube. You actually see the secondary mirror reflections bouncing around the interior of it. So we're doing some pretty cool stuff with the vehicle since we got it to orbit. And we've even done some even cooler stuff. What you're looking at here is actually frames of Sapphire with respect to NeoSat we took last summer. So we're starting to do some very, very neat, tricky stuff with the vehicle since we got it to orbit. What you're looking at is basically NeoSat and Sapphire launched on the same rocket, so they more or less have the same orbit. Except one is slightly lower in altitude, by about 500 meters or so. So one satellite kind of shoots ahead of the other and does one lap around the Earth before the other. But every 14 months, they get close to one another. And in this instance, myself and Stefan Dorstenson, my colleague who works with me on NeoSat, we said, you know what, let's take a few shots at Sapphire to see what we can see. Well, we overexposed it, we couldn't see anything. But we were successfully able to track it, and we were able to actually get the tracking data off of these frames. The Sapphire was anywhere from 8 to 50 kilometers away when we took these frames. So we're starting to try out a new area of space surveillance that very few have been able to do in orbit right now. This is actually very timely because we're starting to see the appearance of basically on-orbit servicing activities taking place in space where you have satellites with robotic manipulators or even just cameras coming up close to other satellites, taking pictures of them, or in some instances, they're actually going to grab them, repair them, refuel them, or do some other exotic stuff. So anyways, we're starting to dabble with that kind of technology a little bit without ever having to launch another vehicle. So it's just a pretty lucky virtue that we flew NeoSat from the same launch as Sapphire. We have two cooperative vehicles that we try out a couple of things. So I'll talk a little bit about some of the astronomical support we've been doing with NeoSat. The original near-Earth space surveillance mission that flew with NeoSat was intended to do some asteroid astronomy by looking towards 45 degrees from the sun. And that mission didn't really go off very well. When we got to orbit, we found that the sensor wasn't as sensitive as we thought it would be. There was noise injected from the solar arrays directly onto the detector that we didn't catch during pre-flight. So unfortunately, that did not pan out. Right now, the University of Bishops and the University of Victoria have taken up the astronomy lead on the NeoSat mission, and the Canadian Space Agency supports their engagement with the vehicle. And right now, University of Bishops is doing some exoplanet detection by following up the NASA test mission transits with that vehicle. Dr. Jason Rowe is looking at basically exoplanet detection detections and doing follow-up observations with the Neosat vehicle. And Dave Ballum out at the University of Victoria is doing some asteroid and comet tracking with the vehicle as well. We're very well placed in orbit. We have this exotic baffle that's beveled on the vehicle that allows us to look very close to the sun. So we can go looking for asteroids that nobody else can. So that's one of the advantages of having the vehicle in place. If anybody's interested, the Neosat data is available on what we call the Open Data Server. If you want to copy down that long FTP address, that's where you can see the FITS files that we generate for Neosat. You can download and play with this kind of data in whatever software package that you have. And so the astronomy data is available for download if you're interested. So I'll talk about one interesting experiment we supported last year. In 2017, there was an asteroid called 2012 TC4. It made this pass by the Earth, and this is by about 44,000 kilometers. So it was a pretty close pass. It was only about a rock about 10 meters wide, had a rotational period of about 12 minutes or something like that. But the interesting thing about this object is that there was a whole pile of ground-based observatories all watching this thing. And the entire exercise was focused on trying to find out, well, let's test the communications pathways between the observatories and the NASA Planetary Defense Office to see how well we can do this kind of job, and see if there was a real collision threat with the Earth, what would happen. We actually learned quite a bit of it. Our job with Neosat was to basically track this object when it was on the day side of the Earth. You can see one track of, so you can see an image of TC4 here on the lower left of the screen. And we track it on the day side just as the object was passing over the South Pacific Ocean. It was a pretty fun experiment. The astronomers, it was my first exposure to one of these kinds of planetary defense experiments. It was pretty neat. When the object was 3 days out, the astronomers knew within 500 meters where this thing was going to pass the Earth. So if this thing was actually going to collide with the Earth, they'd pretty much know which country this thing was going to hit the atmosphere of. So it's pretty impressive what you can do with that kind of data when you have a little bit of time to play with it and so forth. So I'm going to finish up showing you some images of Comet 46P Rickenton. We took observations on that comet before the apparition in December, pretty much every week since October of this year. You can see a little bit of the tail starting to form on these images here, but notice that the object doesn't quite follow a straight line in the path in its images. That's because of the parallax of Neosat's orbit. Neosat does this big orbit around the Earth, and since the object is in the near field compared to the stars, it does these little bunny hops compared to the stars. And basically, the minor planet astronomers love that kind of thing because it's basically the same as 3 days worth of tracking data all compressed into one orbit from Neosat. So it works out pretty well for us. You also notice that there's something else in the background. See that speckling that you see there? Those are radiation hits on our detector. Those are high-energy protons that are basically bombarding the Neosat instrument continuously while we're on orbit. And occasionally you'll see this little snowstorm flare up every once in a while. That's Neosat flying through a particularly hot area that's centered over Brazil, where there's a feature called the South Atlantic Anomaly, where there's basically a short circuit of high-energy protons from the magnetosphere right into our upper atmosphere. And you'll see it appear as that snowstorm event from time to time on the images. So I'll just let that play out here, and I'll be happy to finish up here. If there's any questions, I'll be happy to take your questions, and I'd like to thank you for the opportunity to present today.
How do you point Neosat?
Well, you have to give it a good kick some days. But usually what you do is you just tell it right ascension, declination, and rolling. That's what it comes down to.
How do you orient it? Do you use gas jets or?
Nope, there's reaction wheels on board. So basically we just spin up little wheels, and the change in angular momentum is what steers the vehicle.
Good presentation, thank you.
When you're deploying a solar sail on a satellite like that, how are you controlling its rate of descent so it's not crossing into the path of lower traffic?
You can't really do that. So that is a very fair question. There is no propulsion capability on CanX-7. Now, the benefit that when they deployed that satellite, it was around 730 kilometers, I think. It was not quite at 830. That's where you don't want it to be doing this kind of thing. It was actually in an orbital regime where the density of objects is much lower. So it actually poses a lower risk of collision, even though you've pretty much increased the size of the satellite 100-fold. So it's actually in a lower density regime when you open up the solar sails. They can change the orientation and spin rate of the vehicle with the sail deployed, but there is no thrusting or no propulsion capability on board CanX-7. So we're relying on Sir Isaac Newton.
You mentioned about UTIAS helping in this. Is there any other organization in Canada working on the microsats or nanosats?
Absolutely. There's a pile of them now, actually. When I started in 2007, there used to be Dynacon Incorporated. Part of that company transitioned into Microsat Systems Canada. What used to be ComDev, they built the other satellite that we funded at DRDC called M3MSat, which is a satellite that listens for transmissions from ships. There's something I didn't know about ships, but they actually talk to each other on this VHF band. If you're sitting in space, you can hear it. And so anyways, ComDev built a satellite to basically listen into that kind of activity. There's another manufacturer from Quebec, and the name escapes me right now. They built the Proba satellite. They're just based outside of Montreal. There's Kepler Communications in Toronto now. And there's also several university initiatives with the Canadian SmallSat, CubeSat project that's kicked off with the Canadian Space Agency right now. One thing that you should really understand is that these small, low-cost platforms have really taken off in the last few years. The economy of this has really changed. We're seeing a lot more smaller platforms that you can just build on a lab bench. You don't need these big, giant hangars with multi-ton cranes anymore to move and manipulate these spacecraft anymore. You can build a satellite in your garage now if you have the time and a little bit of cash to do it. You can do that kind of thing. Launch costs are about $50,000 a kilogram, and if you've got your pockets deep enough, and instead of buying a Winnebago, you can buy yourself a launch non-SLU frigate. So it's an option.
Just a curiosity question. If we didn't launch any more satellites, how long would it take for every satellite we have now to deteriorate?
Well, the ones in geosynchronous orbit, they'll be up there for about 15,000, 20,000 years. The ones in low Earth orbits, here's where I incriminate the government of Canada, actually. The NeoSat will basically stay on orbit for about another 80 years. So it will be up there for a long time. The lower in altitude you are, the spacecraft will re-enter quicker. So anyways, that's basically the rule of thumb. If you're under 650 kilometers, for 9 times out of 10, the satellite's going to re-enter in 25 years. But if you're at 800 kilometers, 100 years is not unreasonable. 1,000 kilometers or 1,200 kilometers, you're talking hundreds of years, maybe even thousands of years.
So just a follow-up question to what you just actually answered. The exploded Chinese satellites, how long do we expect it to really be in space? And also, is the risk of collision with other satellites going to increase or decrease over time?
The thing I want to see, intercept that happened in 2007, the entire global community has to worry about that now, even the Chinese. After that intercept occurred, there was an instantaneous increase of about 3,000 objects that we can track as soon as that event occurred. Some of those objects, they actually re-entered within half of an orbit. Some of them re-entered very quickly. Others will be up there for probably several hundred years. But others are re-entering. Every day there's one object that re-enters, either it's 701C debris or other objects that were put in orbit by the US, Russia, or any of the other nations that all participate in this environment. So it depends on the altitude and the shape of the orbit, but if if I was an average thing in 1C degree object, it could be 50 to 150 years, depending on the size and the mass of the object.
All right, one last question.
Well, thanks. We're just wondering.
Just curious if you have a way of tracking like high-risk artificial objects that have been launched into space, like their deterioration of their orbit and their risk factor. Is there a way to account like for the trajectory that they're taking, the rate that they're degrading, and how the atmosphere affects the drag, and maybe like a time scale if they're possibly artificial objects in orbit?
I guess just rephrase your question just a little bit, and maybe I'll make sure I get the intent right. Is there a certain class of orbits that are more riskier than others, or harder to track?
Is there a way essentially to track, because I guess we have more things in orbit than we can actually track at the moment. But I'd like to account for these items that essentially die in space. Is there a way to track how many these objects are and if they'll interfere with other things in orbit?
I guess I'm interpreting what you're asking.
So like,
If I had to pick one class of orbit that's hardest to track right now, it's actually the very eccentric Maya style satellites or geosynchronous transfer orbit. They're very, very elliptical, and I think everybody here knows that adage that basically something that goes up high and comes back down again, it tends to dwell and sit there at its apogee for a while. That's the same in astrodynamics. Anything that sits at its apogee for a long period of time will dwell up there. We can't look towards the sun, so anything that's eccentric and has its apogee up at the sun is very hard for us to track. Then it zips into the Earth, goes through low Earth orbit environment to a very high drag intensive and high density atmosphere environment, to which we can't really track very effectively because it's moving so fast, even the space-based or ground-based sensors can't track it. So there are classes of orbits that are much more challenging because they're very, very hard to track simply because they cross different orbital regimes. The eccentric orbiting objects are the ones that I would pick right off the bat. So does that kind of answer your question there?
Yeah, it does. So there's some objects that are easier to track than others, but for certain orbits it's going to be more difficult to track because of obviously unable to observe because of direction towards the sun.
That's right. I mean, some of them cross different orbital regimes. When you're in close to the Earth, drag is a very, very big deal. Drag is a witchcraft, basically, in astrodynamics. We don't really know what the density of the atmosphere is because there's so many different influences that affect it. But then when it goes out to apogee, you don't worry about drag anymore. Then you have to worry about this pressure from the sun, believe it or not, which is very gentle and persistent, but it's there. And you have to account for that. And since we're in space, these things get nudged around by the sun, believe it or not. And if we don't have the cross-sectional area modeled correctly, we have a very wrong answer very quickly.
All right. Thank you very much.
Hopefully it works right.
Oh, yeah, it's perfect. Thank you. Yeah, thank you. It was a very interesting presentation. Thanks for taking the time to present for us. All right, so we're going to go to break. We have calendars for sale. There's, I think, 5 or so left, so hopefully they're all gone so that somebody doesn't have to take them home. So it is 8:19. Let's meet back at 8:30 to get the second half of the meeting going. Alrighty, let's get second half of the meeting going. So first up, we're going to have Dan Vasu. He's going to take us through some outreach that he was a part of internationally. Dan?
Thank you. Thank you. I'll start with a short intro. I've been a member of Ottawa RASC for almost 2 years now, and thanks to the organization and the amazing people I met through this club, I progressed from knowing basically almost nothing about the sky to knowing quite a lot. And my next few slides will just show how the support that the Ottawa RASC provides to basically anybody who has an interest to astronomy. It's the right place to come. In this slide, I guess you recognize the Starfinder charts that usually Mike hands out to public outreach. And there's this magazine related to meteor showers that I got from another RASC member, Pierre Martin, who most of you know is very passionate about the meteors. And somehow these materials ended up supporting an astronomy event in a Romanian school in Bucharest. My girlfriend is a teacher in Romania, and she teaches grade 2 kids. She also has an interest in astronomy, and she thought of doing this extracurriculum activity about astronomy with the kids. And I had these few materials from the local club here, and I thought they would be useful. And she was wondering in the beginning if maybe half of the kids would have any interest in this, but in the end it turned out they were all very excited and captivated, and it was a big success. And I guess the next few pictures will prove it. I think this is all I have, and basically with these slides I just wanted to show you that your support can reach far away, and you may not realize it sometime, and like in this case, few thousand kilometers. And so keep doing the good work, and thank you.
Yeah, thanks so much, Dan. That's it's fantastic to see sort of the faces of all those kids lit up with excitement about astronomy. It's good to start them young, they say. All right. Up next, I'm going to be calling on our past president, Tim Cole. It looks like someone didn't remove him from the auditorium after all. And he's going to be he's going to be taking us through the excitement of the upcoming lunar eclipse. Tim, take it away.
Yes, okay. Sorry. Well, happy perihelion, everybody. All right, that went over wonderfully. Okay. Observing the next lunar eclipse, which won't look anything like this because it will be cloudy.
Yes. No. No. Positive.
Yeah, I am positive it will be cloudy. Okay.
No one buy any equipment between now and then, please.
Yes, exactly. And and returning it doesn't count. Yeah, there we go. That actually is a really nice picture of an eclipse from Athens, which happened to be a central eclipse. And I'm hoping we'll have something that will be just about as nice in terms of a nice rosy color. I like that color better than practically anything else. The really pitch black ones are kind of a pain in the butt. There we have a little timetable of it. Anybody who says they can see a penumbral eclipse, yeah, never mind. But the umbral is always good fun. And as you can see from here, we're fairly close to the center, so we've got a reasonably long central portion, which is a little on the dull side, but you can actually get a fair degree of change in the color and tone during the totality. So it'd be interesting to see what happens, and that's partly what I like about the color. I put some timing on this. You'll find that this timing chart is used in all the standard eclipse documentation, going from the penumbral stage 1 to the penumbral stage 4, and you'll find that all in most of the standard stuff. However, what you'll also find is first, second, and third, and fourth contact with respect to the umbra. So I think that's the most useful because nobody can see a penumbral eclipse worth mentioning anyway. Ingress and egress, to my mind, are always the really fun bits because it's dynamic. You get to watch some intriguing stuff. This, I'm sure most of us already know this, but this is going to come up. People will always wonder why. and how it works and why you've got a penumbra and an umbra. So just the basics of it. We're getting the penumbra and umbra because we've got a distributed source, and it's exactly the same effect that you get from seeing a light cast, a shadow cast by your door in your office. Same effect. Yeah, I'll leave it at that. We have different classes of eclipse. So we can get anything from a partial penumbral, where, as far as I'm concerned, that doesn't exist. Penumbral, which almost doesn't exist. A partial umbral, which is a tease. But actually, I mean, you can still have fun with that. The umbral and then the central eclipse, which does not mean, incidentally, that the center of the moon has to go through the center of the umbra, just that some portion of the moon passes through the center. They don't have to coincide. It's drawn that way because I'm a lazy cuss and it's easier to draw it that way. The next one you'll get, I know this is probably going over stuff for most people, but I find you get this when you explain to people that the geometry of the eclipse. The next question that you'll get is, well, why don't you have it every month? And the answer is fairly easy. The moon's orbit is inclined, and you have to wait for the lines to interact. The analogy I always use is taking a coin and spinning it. Just like when your spun coin goes wooga, 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 wooga before it falls on the table, it's the same thing here. So if that comes up, that's just your quick answer. It's inclined about 5 degrees, and you have to wait for the lines of nodes to cooperate. And you can see with this one, the simulation is showing the shadow of the Earth. Illumination, every now and again, you'll notice a slight blue tinge on the outer portion of it. And the thing with that is, in the upper atmosphere, the ozone layer tends to absorb a fair bit of the red, and what's left gives you a subtle bluish tinge. And then for the lower portion, you're getting the red illumination. How much of this depends on everything? How much crud is in the air? For example, back in 1992, after Mount Pinatubo did its thing, that particular total lunar eclipse was pitch black. You could more easily find the eclipse by looking for where the stars weren't, because the moon was that dark. So I'm hoping we'll go for the next stage. And along that line, you can only assess the depth of it after the fact. So a fellow named Daniel came up with his scale going from pitch black, which I find a bore, to copper orange, which is fun, and you might get the bluish. I kind of like a level 3, because I think it's fun, for no other reason than that. Crater timing you can do if you want, as you watch the shadows go for and go across the surface of the moon. Interestingly enough, there's some value to that, because as strange as it sounds, we don't have really good models of predicting the exact width of the umbra. It depends a lot on atmospherics, so having that data around is useful for doing analysis of how the atmosphere behaves. You will find timings for this in the Observer's Handbook, or else in MrEclipse.com, any of the standard eclipse stuff. And if you were to see it from the moon, because again people ask, well, it's sort of that. You'll have a little bit of red light from the Earth, and unfortunately I was too lazy to get rid of the glow that Starry Night puts in for the sun no matter what. You wouldn't actually see that on the moon, of course. But it's better than having the lens flares that you normally get. So again, this is just sort of fun. It's something people have asked a lot, so I popped it in for us. We are setting an event up here, weather permitting. That's it. Jesse's ruined it for everybody. He's put in weather permitting, which wrecks it completely. So we've got some spots set up here. It is fairly late, as you'll notice, so we're not entirely certain what kind of a turnout we'll get. And almost certainly it'll be just for ingress. By the time totality starts, most people will just take a hike and go home. Again, we'll be doing that here, so we'll be doing the usual, looking for volunteers to come out and do whatever cloud reduction dances seem appropriate. So enjoy the cloud cover that night, because everything should be just... I'm trying to put reverse English on it. So we'll see. All right, everybody, do enjoy the eclipse. Hope we get a nice one. That's it. I'm out of here.
Thank you. Thanks, Tim. Just gonna go back a couple slides here. Just because ever since Paul pointed it out, I can't unsee that damn deer. The damn deer. The deer that Paul mentioned. Eyes, nose, antlers. I still see it every time I look at the moon now. You've ruined it for me, Paul.
Sorry.
And I guess what's interesting about this slide is, I guess from the moon, it would be a solar eclipse. Yep, exactly. Which is cool. All right. Observation reports. We've got plenty this month. So if you're on the magic list, if you could get in line over here. And we will be starting with Taras.
Happy New Year, everyone. Comet 46P Virtanen has been traveling across the southern skies. Oh, there you go. In December, and those rare occasions when the sky was clear would give us an opportunity to enjoy the sight of it. The picture was taken on December 8th from Bob Olson's observatory in North Augusta, who was very kind to host me and Eric May that night. Despite the brightness, and in particular, it has reached the magnitude of 4.2 on its closest approach to the Earth. The comet was rather, as you can see, was pretty dull, and it didn't have any prominent features, except, well, for the bright coma. There is a hint of the tail kind of stretching like this a little bit, but well, it was a moony light, and it was not really high enough in terms of the contrast of the sky was pretty low, so it didn't show up well. Here's an animation. So the comet this was taken when the comet was between Cetus and Eridanus that night, making its path toward Taurus. The time-lapse animation, this one consists of about 15 minutes of frames taken 30 seconds each, with the interval of 30 seconds. So this comet makes an approach to flyby of Earth every 5.4 years, which means that we could observe it again next time in 2024. So these constant swings around the sun come with a cost, because every time when Virtanen makes it through this close to the sun, the ice that it consists of melts, and what's left is not enough to create a powerful tail or a visual tail, because it's been doing that so many rotations, so many times, that everything which would produce the tail is already blended in, and that's one of the reasons. Also, as you can see, so this was taken, the screenshot is actually of January 1st, when the comet was a bit of a distance from the sun, while the closest approach was here on December 16th, when we could see this pretty bright and amazing location next to the Pleiades, actually. Pleiades on December 16th were perhaps this close to the comet, which was traveling this way. And this would compose a nice picture, but unfortunately, as we all know, it's not our luck to see the clear skies that day when we need it. And this was taken 2 days later, when the comet already traveled quite a distance. However, these about 20 minutes of exposure altogether, I'm happy that when I started actually stacking it, I didn't realize that there is another object here, which is the California Nebula, and dark lanes of dust is a bit seen here. There is dark nebula here, but I'm not sure if it's actually part of this darker stretch of space dust, and Aldebaran here. This was taken on November 24 from Laval, Quebec. The ISS transits over the face of Moon and Sun happen relatively often, but you have to be in a specific area in specific time to see its full, which is not really completely full, but pretty wide extent. This particular one happened around 12:30 a.m. and features 0.6 second duration of the transit and almost an arc minute of ISS angular size, which that time resulted in 17 frames, which I stacked later on and superimposed, so each frame is 1/30th second of video taken of that transit. Now, the seeing was not too good. I wanted to improve the image a little bit, so the background is actually stacked, and so I did with these 17 images, stacked them together. I thought the quality will be a little bit better, but it's still pretty fuzzy. So I showed this picture to my friends, and they said, well, I don't, some of them said, well, I don't even think it's ISS. So I Googled this image, and apparently it's called a twin ion engine X-1 fighter manufactured by Cyanide Fleet Systems. Have to be true. Thank you.
Thanks, Taras. Well played there. All right, Rick Wagner, you're up next.
So before we get started, show off my new socks. Astronautics, planets, astronauts.
You want the light? Step into the light.
Step into the light. So, not often I take time away from my photometry to take a picture of a galaxy, but since there's a new excuse to take a picture of this galaxy, and I talked about it last month, this is M77. And you remember I said it was one of the difficult ones to observe. You can see it's got a really bright, very central nucleus. And under city skies, this is kind of about what you'd probably see. This is about a half an arc minute wide. The guidebooks say that it's 6 by 7 arc minutes. It's 9th magnitude, so it should be easy, right? Except all the light's concentrated into that star in the center, which is actually its active galactic nucleus, which is a supermassive black hole doing all sorts of exciting relativistic things. So with all the light concentrated in there, it doesn't leave much for the rest of the galaxy. So under poor conditions, you're actually looking for something that's pretty small. So if we take a longer exposure, you can see this is yet more of the galaxy pops out. Nice disk with nice spiral arms. That's the supernova right there, so that's why I was actually taking the picture. And the only record I have in my observations of this object is in fact 3 arc minutes wide with a stellar core. That was from Fred Lossing Observatory back in 1990. In fact, almost exactly 21 years ago, New Year's Eve, 1997/8. So you can tell what an exciting life I live when I'm out at the observatory on New Year's Eve. So then if we stretch this picture even further, this is only a half-hour total exposure, so it's not great. But you can see there's a whole bunch more galaxy. And this is the 6 by 7 arc minute thing. So it's pretty faint. I was out Tuesday or Wednesday night with my 12.5 inch and with the Boltwood 40 centimeter, and, you know, under dark skies. They're both showed it quite nicely, but it's definitely a challenge object. So, thank you.
Thanks, Rick. Next, we've got Richard Taylor. Advance the slide. That one you can use a pointer at the top button if you like.
Okay, so I had a little bit less success with my comet pictures. I was inspired last month by some of the pictures people were showing and thought that, oh, maybe I can get a picture of that with my telephoto lens. But first I had to try and spot it with my binoculars, and every clear night we had, those few that we did have, couldn't see a thing. So then I noticed in the plot of the path of the comet that the night after the full moon this month, or last month, the comet was going to be really close to Capella. So I thought, this will make it easy. I can find it. So I get all my equipment together. I find out when the moon's going to rise, and 5:40 was the moon rise. So I said, okay, I've got, you know, maybe 20 minutes. I can get out there and get a picture of the comet. So I get out to the experimental farm. It's cloudy again. I got a nice picture of Arcturus, because that was the only star I could see up in the sky. And I was fiddling with the equipment, trying to get it. And then I noticed this big red glow in the east. So shifted the camera around, and that's what I got. It was a beautiful moon, but I never saw the comet that night. And then, of course, Christmas intervened. There were a couple of clear nights, I believe, but I was kind of busy with other things. So it wasn't until the 29th of January. My brother was having a party at his house near Athens, Ontario, and I thought, okay, it's going to be clear tonight. I got to take my equipment with me. So I head out, leave the house during the dessert, and whoops, that is what I saw. A beautiful clear night. We've got the Pleiades up here. We've got Auriga down here. And the prediction was that the comet should be somewhere over here on its way towards the Big Dipper. Can you see it? Well, I sure couldn't with binoculars. I think it wasn't until I got back in the house and looked at the picture, but yeah. You got it. It was there. So once again, I was having some problems aiming, but I took pictures all over the place in the region that was supposed to be. And finally, when I got home and processed them all together, that was my best picture. So I did get the comet. Now, naturally, of course, there's so many stars in the sky up there that it was very, very difficult to spot visually. It was not a very prominent comet. So that's my best attempt. Thank you. Oh, sorry. Yeah. While I was out there, I thought I can take something I know about. So there's the Orion Nebula, too.
Was that a meteor in the upper right-hand corner?
No, just an aircraft or something, I think. Satellite, maybe.
Right there? Might be a meteor. Oh, right there.
To be fair to Richard, on the computer screens back up here in the booth, there's a really clear meteor.
Meteor. Okay.
All right. Thanks, Richard. All right, up next we've got Jim Sophia.
Thank you. There we go.
Now you got to aim it at the booth. To the booth.
Okay. I did not take this shot. However, it's sort of an introduction to M66 that I did take, but I'd just like to begin with this introduction. So this is, in the constellation Leo, this is an image of the Leo triplet, and it's composed of NGC 3628, M66, and M65. And through a wide-angle eyepiece, this is really a treat to look at. I'm sure some of you have already seen this. It's quite nice. The distance between M66 and M65 is 20 arc minutes, or approximately 200,000 light years. And the distance among the three is close enough to have involved some previous gravitational interaction. And what I'm going to show you is some of the reported effects that the gravitational interaction between NGC 3628 and M66 occurred about 1 billion years ago, apparently. And so, all right.
It's the one on the right.
Oh, there we go. So this is a 16-second exposure of M66 that I took a number of months ago with the Malincam exterminator. M66 is the brightest and largest member of the Leo triplet. It's approximately 36 million light years away, and it has an apparent magnitude of 8.9. It's known for its outstanding dust lanes and spiral arms. So apparently, a big-time gravitational interaction between NGC 3628 and M66 occurred about 1 billion years ago. And as a result, the structure of M66 changed. And apparently what had resulted is that this galaxy has had its bulge slightly. The bulge of the center is slightly off to the side. It has a high central mass concentration, and its arms are asymmetrical, with a clump of interstellar cloud of neutral hydrogen that apparently was removed or disrupted from one of its spiral arms. And as a result, the galaxy appears to have a conspicuous and unusual structure of spiral arms and dust lanes. And the distorted, hooked spiral arms that you see, I believe, right over here, right over there, apparently has been displaced and is operating above the plane of the galaxy's disk. So for these oddities, and for this reason, Alton Arp included M66 in his Atlas of Peculiar Galaxies. Another interesting trivia item for M66 is that up until now, 4 supernovae have been detected in M66. The brightest of these at magnitude 12.2, which was discovered 30 years ago in January of 1989. Thank you.
Thanks, Jim. All right. Up next, we've got Gary Boyle.
Thank you, sir. Happy New Year, everyone. Well, the morning of question, December 16th, it was cloudy till about 1 a.m. I kept watching the app for and the clear sky chart, and it said 1 a.m. could be 1 block, 1 hour. So 1 o'clock it was. Went outside. It was clearer till 4 a.m. So I was able to get the comet next to the Pleiades. Just as a little three-dimensional, the comet was about 11.5 million kilometers from Earth. The Pleiades 450 light years from Earth, and a light year is 10 trillion kilometers, give or take. So took this on my old, Canon Rebel, the 450 or D450, 450D. It was 7 images of 90 seconds,
stacked together on 135 millimeter fixed lens at about f3. So I'll use the deep sky stacker to stack them, and elements 10 for the processing, along with biases and flats, which I'm finally experimenting in, so it really makes a difference. So I can take a comet off my bucket list, especially up next to Pleiades. Really happy with the shot. And I hope a lot of people got to enjoy the comet to any extent, even in the paper, whatever, online, to see something this close, this bright. Seems to be, we get a lot of Christmas comets. We had Comet Lovejoy a few years ago, again, next to the Pleiades in December, January. So who knows when the next one will be. And let's hope we have clear skies for the eclipse coming up. Thank you all.
Thanks, Gary. That's a fantastic shot. All right, up next, we've got Paul.
Thank you, Oscar. Well, season's greetings to everybody. I'm glad to see a bunch of you got out to see the comet. There we are. December was challenging. I don't need to tell you that, but it was pretty challenging. The opportunities that we did get a few clear nights, but they turned out to be, at least out in my neck of the woods, more like glorified sucker holes that lasted for a few hours, as Gary pointed out there. So you gotta, if you got them, smoke them, basically. Take the chance while you have. The comet is still visible, but what I thought I'd do is, for those of you that didn't get a chance to see it, I've got a collection of shots here that I did take through those sucker holes, and so you don't miss out on it. Interesting with Dr. Scott's presentation there, the last video that he was showing showed you the comet up until December the 2nd. And as Dr. Scott pointed out, very little in terms of a feature within the comet itself, like no glorious tail or anything, but hints of a tail. This is a shot I showed you last month. It was just taken 2 days before the meeting, and you can just see a little hint of a tail there, but basically a glowing sphere. So that was December the 5th. And so I tried to get out on every sucker hole that we could, because I knew this comet wasn't going to be visible for very long. So a couple of days later, on the 10th, managed to get that with a 300 millimeter lens with a 1.4 extender on it, so 420 millimeters. And again, you can see basically a very spherical coma, quite bright in the center there. And but no really obvious features there. So I was crossing my fingers for December the 12th and the 16th. December the 12th was when the comet was at perihelion. 4 days later, closest approach to Earth. And as it turned out, I did get a lucky break on the 12th, the night of the perihelion. And so I managed to put the 11-inch Edge HD on it, and so we zoom in on that, and we can have a look. So that's the night of perihelion, and you can see that there is a bit of structure there. This is all within the coma, as you saw from the previous shot there. The streaks that you can see there, I did remove the stars, much the same as Dr. Scott was talking about with his work. Did remove the stars there so we could just focus on the comet, and you can see that there is structural detail in there. Just to give you a sense of scale, too, about this object, the original photograph here is 3,000 pixels across. The nucleus itself of this object would be 1/20th of 1 pixel in the center of that bright spot. So just to give you an idea of how small the actual nucleus is. This next slide is going to be a little harsh on your eyes there, but I wanted to do an inverse of this because it's a little easier to see the detail, so stand by for retina fry. So there you can see, it's the same image, just done inverted so that you can see the structure of what little tail there was there. You can see there's a definite elongation along that path with a general kind of a fan-shaped brightening there. And at the distance of the comet on this night, which was 11.9 million kilometers, you can see the scale of that. of that bright area there, or the central coma there, about 10,000 kilometers across at that scale. The nucleus is about 1 kilometer across. So yeah, it's pretty tiny. So that was December the 12th, and as Gary mentioned, we really lucked out on the 16th because, at least in my neck of the woods, I was watching, like Gary, was watching the clouds all day, and was wondering if we were going to get a shot at this at all because the placement was beautiful with the Pleiades. And same thing that happened to you. Basically, at about 12:45, it cleared out, and managed to bag a nice wide-angle view with a 16-millimeter lens. So you can see here our friend Orion there. You can see some of the red nebulosity there, the Hyades there with Aldebaran, Pleiades there, and our friend the comet. You can see a bunch of other features there. There's the Rosette up there, or the California Nebula, and the Rosette up there as well there. So that was very fortunate. It was a little bit later than I'd hoped to be shooting. I was starting to get down into the trees there, but I thought, oh, I'll leave the trees in there because they look kind of cool. So on this night, it was for that sucker hole when it opened up, it was very clear, and the seeing turned out to be actually really quite nice. It was easily visible to the naked eye, at least out in my neck of the woods. Obviously, with binoculars, it was just a gorgeous sight there. So I did have 2 cameras rolling. I had the 16-millimeter lens here, and my last shot was with a 135, and it cuts in on that area there, just so a bit of a closer view. And there we go, December the 16th, night of closest approach, about 11.5 million kilometers away. So we did get lucky. I did see this thing, this comet, just a few nights ago, so it is still visible. Whether it's naked eye, even under a dark sky, is a little bit questionable. It's now about twice as far away from the Earth as it was on this night. But I did see it in the binoculars quite easily. So if you haven't seen it, and we do get a clear night, we're in a moonless window now, it would be a good time to check it out if you really did want to get an eyeball on this thing. And I thought it might just be at the threshold of visibility, but especially for younger eyes. Thank you very much.
Thank you, Paul. All right. We're going to move on to our observing challenge. So I didn't propose any challenge in December, just because I figured everybody would be busy with the holidays, etc. But the challenges from November were these there, the M31, NGC 6888, Stefan's Quintet, and Mons Hadley and Rima Hadley. For this month, as our beginner challenge, folks should go out and look at the Orion Nebula. It's a star-forming nebula in the constellation Orion. It forms part of the Sword of Orion, hanging just off Orion's fashionable belt. Easy object in binoculars and a wonderful object to look at in any telescope. For our intermediate challenge, I'm proposing people look for Able 12, which is a planetary nebula in Orion. Magnitude 13.9. It's about 37 arc seconds in size, and it's quite close to Mu Orionis, so it requires quite a clear night, so you're not struggling against the glare of that star. And it may help to use a UHC or O3 filter to help you out. And for our advanced challenge, I misspelled Able there, but Able Galaxy Cluster 426. It's a galaxy cluster in Perseus. There are many galaxies in this cluster. Let's see how many people can spot. But there are 18 NGC objects, 11 UGC objects, 6 IC objects, and 1 PGC object. So quite a few galaxies in that cluster to try to hunt down. And for our lunar challenge, we're going to do craters Armstrong, Aldrin, and Collins. So they're located within the Mare Tranquillatus, near the Apollo 11 landing site. It's best viewed on lunar days 5 and 19. Armstrong crater is only about 5 kilometers in diameter. Collins and Aldrin are about 3 kilometers each, so you'll need probably a fairly like an 8-inch or larger instrument to be able to resolve those. All right, so there are the challenges again. The Orion Nebula, Able 12, Abel 426, and Armstrong, Aldrin, and Collins. All right. On to the FLO star parties for members only. The next one is January 5th, weather permitting. I haven't looked at the forecast for tomorrow, so anybody know what that's looking like? Bad? All right. Probably not going to happen. But maybe we'll get all the clouds out of the way now so that we can enjoy the lunar eclipse rather. Estelle's pick of the month, Universal. So you can see her and our library just behind the stage here to the right. Here are some of the folks that help keep the club running. As always, our meetings are recorded and available for viewing in our archive on our website. Thank you to everyone that attended. There were 98 attendees tonight, so thanks very much for coming out on a January evening. Thanks to all the organizers and speakers. And once again, I'd like to wish everyone a happy new year. We're going to have our post-meeting meeting at Grace O'Malley's again. So come out for to wet the whistle and maybe have a snack and some astronomy chat. I did call them, and they are not having any live entertainment tonight like they did the last time. So that's right. Our next meeting is February 1st. We've got a couple pretty interesting talks. Dr. Janet Tulloch, one of our members here, is going to be giving us a talk entitled Outstanding Standing Stones and how they relate to astronomy. And also we're going to have Jesse Rogerson giving us sort of an overview on the Juno spacecraft and its mission at Jupiter. So those will be two talks that should not be missed. Some of the benefits of joining the club: you'll have access to the Ted Bean Loan Library, where you can borrow a telescope or two and take one out for a spin before you decide whether or not you want to buy one. Get access to our book library and also access to the Fred Lossing Observatory. Additionally, you'll get some interesting publications. Sky News is included with membership, the RASC Journal, a copy of the Observer's Handbook every year, and of course our very own astronauts. All right, and the moment you've all been waiting for, door prizes.